Is it moving? No. Yeah. Okay. So I'll actually ask 3 ice-breaking questions. First one is very easy. Second one is medium. Third one is slightly more difficult. Okay. So what is the ice-breaking question? That's not the question. So the question is this is a talk about 2 tails, and you see this picture. Which poem does it correspond to? It's written by the person Shukumar Ray. It's written here. It's a very bad question, perhaps it's biased towards Bengalis, but still, anyone can try to write in the chat, and if it's done, then Jyotishko would let me know. Has anyone, want to guess? No one's participating? It's too early in the morning for the people in USA or something? Somebody wrote something in the chat. What is it? Yes, I think people are doing it. Okay, good. Very good. The answer is Huko Moko Hangla. Say the non-Bengalis, I apologize to you. I have questions for you too, don't worry. Okay. So this is a poem, a satiric poem called Huko Moko Hangla, which makes, okay, let's not get into the meanings, but which has, this guy has 2 tails, and that's why I'm referring to this in this talk. Okay, so I'm going to talk about how to tell a tale of 2 tales, and these are all my collaborators, among which Ayan Bhattacharya was my PhD student. He's now in IIT Bombay. And then Shobik Ray is actually in Stanford as a PhD student, but when he did the work that relates to this, he was a master student. This was his master thesis, essentially. Okay, so what is my actual ice-breaking question? So the first thing is that there is a movie, I would say a series of movies that relates to today's date. Can anyone tell me what the movie is? That's my second ice-breaking question. This has nothing to do with my talk, by the way, this question. I just realized that today's date is related to a series of very bad movies, I think. But yeah, very good, Friday the 13th. Now here goes my third ice-breaking question, which I don't want you to answer right now. It's a very interesting question. Show that every calendar here has at least one Friday the 13th. It's not a very difficult problem. It's, as you know, how the days go modulo 7, right? If first of a month is Friday, then, sorry, say Thursday, then 8th of the month is again going to be Thursday and so on. So using this 7 modulo arithmetic, you can solve this problem. But do solve this problem. This has nothing to do with this talk, except that it's just coincides with the date. Okay, now let me come to the point. What is this talk about? So this talk is about what this model called branching random walks. Now, there are 2 distributions called progeny and displacement distributions. Their tails are the ones I'm talking about. The key question is that how do these 2 tails affect the branching random walk? This is the key question. Now, we'll try to answer this question in a very, very special case. I'm not going to really tell you about 2 tails, honestly. I just wanted to give a catchy name. That's why I gave it. But honestly speaking, I'm just going to talk about a very special case. Okay. Even though I'm going to talk about a very special case, let me give you the model in the most general case, and then I'll specialize to a very special case. So what is the branching random walk? So roughly speaking, a branching random walk is a growing collection of particles that starts from one particle, and then they branch and spread independently of their positions and other particles. Now, this doesn't say anything. This is like a completely vague statement. I'm going to make it more precise. Now, what I'm going to assume, and this is a toy model. Physicists call it a toy model. So we'll assume that there is no interaction between the particles, which means particles do not collide, or they don't club together to become one particle, or they don't explode. These kind of things do not happen. We're also going to assume that the particles sort of can cross each other without colliding. So everything will happen on real line. We'll think of it like instead of real line, we have a very thin strip, and your particle is so thin that they can cross each other without repelling or attracting or anything like that, or killing each other, or exploding or anything like that. The question is, what is the long run configuration of the positions of particles? Which I think is a very vague question at this point. We'll make it more precise as the talk goes on. Now, this model was introduced by Begins in 1976, exactly 2 years before I was born. But then the background work was done by Hammersley and Kingman in their papers in 1974 and in 1975, respectively. So whenever people give a talk on branching random walk, they always refer to these three papers together. Now let me now tell you the dynamics. So now it may make it more precise. So I'll start. What will happen is I'll tell it in a physics language. So I'll talk about particles. But anywhere I use particle, you can replace it by a bacterium. So it will become a biology model then. Okay. So anyway, let me use a particle language. So start with a single particle, and then every action is happening on the real line. So we have a real line on the real number system. You're having some action. So what is happening is you start with one particle at the root at time 0. My time is going to be discrete. So you can think of them as epochs, if you will. At time 1, what happens is this particle branches into or splits into, instead of branches, you can say splits into a random number of particles, 2, 3, 4, 0, anything. It can also just die off and not branch into anything also, okay? Into a random number of particles following a distribution called a progeny distribution. And then each new particle makes a random displacement on real line independent of each other and also independent of the branching. Now, how many particles were born also is independent of all of these displacements. And these displacements are happening with respect to a distribution called displacement distribution. So what's happening? You had one particle to start with. It split into, say, 3 particles, like in this picture at time 1. Each of these 3 particles, independently of each other, makes some displacement according to some distribution. Okay? And then distribution, these displacements are also independent of how many particles are born. So if there are 2 particles, same distribution is the displacement distribution, is independent of the number. And this goes on. At time 2, you have now 3 particles. Each of them will now split into a random number of particles. And each of those new particles are going to now make a displacement from where it was, where the parent was. Okay? And this dynamics is going to go on. This is going to give rise to what is called a branching random. So before I move on, is the model clear? Is there any question on the model? So if there is nothing on the chat for like...
I have a question.
Yes, go ahead.
Yeah. So how are you defining the displacement? Like from which point?
Very good question. I was expecting somebody would ask this. Not every time this is going to happen, but I have a slide for your answer right after this. This was Alokesh, right?
Yes.
Okay, thank you for the question. Alokesh was my student at ISI. So anyway, so the thing is, I'm going to tell you very soon. So next slide will answer your question. But before I answer the question, let me just tell you that I'm drawing this picture like this, telling you which particle came from which particle, whose parent, whose grandparent, etc. But when you actually see the thing, you will see a snapshot. Namely, at times say t equal to 3, you won't see anything what has happened before. You're just going to see these particles. You don't know who are cousins, who are brothers, who are siblings, etc., etc. These kind of things you won't know. You just know that they're just all there. So you don't know the genealogy. In particular, you don't know, for example, these two are siblings, this point and this point. Can you see my cursor? Yes, right?
Yes,
so this particular point and this particular point are, they are siblings, offsprings of the same parent. You won't understand that. You won't even understand that these are cousins of which order, etc. You won't know that. So you will just see this guy. Okay, and you have to, whatever that is there, from there you have to conclude. And what I mean by point configuration in the long run is that when you run it for millions of generations, say, how will this whole system look like? At 3rd generation, okay, by the way, time and generation, I'm going to use interchangeably because you can think of this as the 0th generation, this is the 1st generation, 2nd generation, and so on. So time and generation, I'm going to use interchangeably. So this is a snapshot of the particles in the 3rd generation. What would be the snapshot in the, say, nth generation when n is, say, 2 millions or something? Okay. That's the question I'm asking. Again, the question is vague, but I'm going to make it more precisely. Okay, so this answers Alokesh's question. Okay, you have more question? I'll just wait for a little bit. So there are 2 things here. One is displacement, another is position. So you see at time 0, this particle was at origin. So this is the origin. Okay. Now, suppose you look at this particle, this red particle that you can see. Parent is here. From the parent, the particle has moved this much that you can see in this picture. So this is the displacement of the particle. So all of these real lines are like, they're just projections of each other. So this is the origin that goes all the way, this point goes all the way and so on. So I've just drawn the same point here. So this length gives you the displacement of this red particle. On the other hand, when I say position, I mean total displacement from the origin. So for example, the position of this particular particle is the position from the origin, how far it is from the origin. So in other words, position of every particle is position of its parents plus the displacement of its own. Okay? And when I say plus, this can be negative also. What I'm adding can be negative also, depending on which way the movement happened. Okay? So for example, here, the movement happened on the negative side last time. So this would be this plus this part, but with a negative sign, of course. Okay? Does that answer Alokesh's question?
Yes, yes. Thank you.
Any other question?
So position at any point in time is the sum of the successive displacements through the ancestors.
Yes, exactly. That I'm going to use later, but that's a very good observation. So I'm going to use this later, but what you can understand this like, if you look at the genealogy of that particle completely, for example, this red particle, this is the parent, this is the grandparent, this is the grand-grandparent. So you look at the displacements of all of these particles, all of these ancestors, as somebody said already, with honoring the sign, you add them up, okay, you get the position of this particle, red particle. Very good observation. I'm going to use it later. Okay, very good. People are going ahead than me. That's always a good sign. Any other question or clarification as I move on? Okay. So they appear in many contexts ranging from physics to biomathematics, etc. It can basically describe how a population invades a new environment. And we are going to consider power law displacements. I'm going to tell you what that means. And they actually arise naturally in ecology. There is this phrase called levee flights. These are essentially, they model how the predator, they catch their prey. What is the distance they cover, etc. They follow some power law distribution. In any case, our simplified model is not going to happen in a jungle, but it's going to happen in a one-dimensional jungle. So that means that we only particles to move and align, not only align, we're going to make sure, we're going to further assume that all the displacements are positive. So it will actually only go towards the positive side of the real line. So it will only move towards a single ray. It's a very simplified model, but more complicated models can be considered where particles move in the whole real line or a plane or a box, etc. Now, for the purpose of this talk, we are going to restrict ourselves to simple model and study what is called the long-run configuration of the positions of the particles. Now, one thing that I want to tell you that, for example, say these are particles and say this is I'm talking about a box, say a room, okay? And then these particles are moving, and then if a concentration of the particle is very high in a particular area, they might explode. So this might be an interesting question. What is the maximum possible, density of the particle in an area? These kind of questions are natural for physicists. If you're a biologist, you don't want too many bacteria on one particular organ. So if it's a bad bacteria, then you don't want too many of them. So you want to see whether there are too many bacteria in a particular region. This kind of questions are natural, as you can expect. These are all part of this long-run configuration. Okay, now this also is important because this is connected to various models in probability and statistical physics. I've listed some. Don't have to worry about the models, so it's not important. The point is that if you Google Zhan Shi plus branching random walk notes, you'll get lecture notes by Zhan Shi, which has, by the way, I think the Chinese pronunciation is Zhan Shaw. Anyway, I don't know, but somebody told me this. So anyway, so you will see the connections to various models, and the introduction to this lecture notes is fantastically written. So you should definitely look at it. So by the way, this Roy is the Rishideep Roy, who is my colleague, but not in ISI. He's in IIM Bangalore, Indian Institute of Management, Bangalore. Okay, so any questions, comments, or concerns before we move on? There is a question in the chat. Yes. I'm going to make it okay. So what I mean is that there is no deflection principle here. I'm just going to take the particle displacements to be positive, just to make our life simple. When it's not positive, there are ways to handle it, but I'm not going to go into it. I just want to present this in a very simplified model. That's all. I'm not going to use any reflection principle or anything like that. Okay, thanks. Any other question before I move on? Okay, so let me move on then. Okay, so two simplifying assumptions, which basically answers the question. The first one is that I'm going to assume that each particle is going to give rise to two offsprings. So in other words, every time it's a binary splitting or binary branching. So that's why this is going to be called binary branching random walk. So in other words, you saw that the whole picture is given by a tree, right? There was a tree representation, and this tree is going to be what is called a binary tree. Okay. Then we'll also assume that the displacements are all IID, so independent and identically distributed. So all the particles, they independently behave with each other. They don't depend on each other. Okay. So they don't care about what the other particle is doing. And they all have the same distribution. Same distribution is a power law distribution. How does a power law look like? The power law looks like, I'm not specifying the distribution explicitly. The only part of the distribution that I care about is the tail. So these are all positive valued random variables, and I only care about the right tail because there is no left tail as such. Okay, or whatever happens near zero won't matter for us. What will matter is what happens near infinity. So what I mean by that is that if D is a displacement random variable, then probability of D bigger than X, which is the tail, right tail of the distribution or the survival function of the distribution of D, that behaves, this goes to zero as X goes to infinity. We all know that, but it goes to zero in a polynomial rate. So it goes to zero in a power law. That's why it's called a power law distribution. Just to warn you, if D is say exponential distribution, this tail is going to go exponentially fast. So I'm definitely going slower than exponential distribution. So in other words, I'm going to have, see if I had allowed say both positive and negative displacement, and I told you that displacements are normally distributed, then my theory is not going to apply. Okay, because that will have exponential tail. Where will it apply? For example, if D has Pareto tail, if D has stable distribution tail, if you know what that means. Anyway, if you don't know what that means, there are other distributions which, like Frechet distribution, for example, which satisfies this, this equation. This is an asymptotic equation. So I'm not specifying the distribution explicitly. I'm just giving you a parameter called alpha. By the way, this alpha is strictly positive. I should have mentioned that. It's a mistake. I'll correct it before sending the slides to Jyotishko. By the way, Jyotishko, I'm going to send you the slides. I don't know whether you guys keep it somewhere. I can just send it to you.
Yeah.
You can email it to everyone or whatever. I mean, put it in the website or something. Yeah,
we can do that. Thank
you. Okay, thanks. So alpha is strictly positive, and then this alpha is called the tail parameter. It's a parameter of this distribution. In particular, we want to know how alpha is going to change or affect the long run configuration of the particles. Okay. Now, such models arise in ecology, as I had said already. Levy flights is a key phrase here. Okay, now important question is, how does the system look like in the long run? What does it mean? It means, for example, how fast the system of particles grow at time n and as n goes to infinity. And what is the quote-unquote scaling limit? The scaling limit is a very big question, but before that, let's try to understand what I mean by particles grow. Particles are growing, as you could see. So if you go back to my slide here, you could see that the particles are growing here. So here, for example, the range was this. Here there was a little small, then it again grew. So if you go on running, you will see the particles are going to grow. Okay. So how is the system growing? For example, how is the range of the system growing? That can be one question. So if you look at the rightmost point and the leftmost point, you look at how far they are. Okay. And then how is it growing? That can be one question, for example. Okay. So all these questions we want to answer. And we want to also find its scaling limit. So I'm going to make sure what I mean by that. Now, since I have assumed the branching is binary, at time n, there are 2 power n many particles. Okay? Because every time you're having two offsprings. So at time n, there are 2 power n many particles. So in particular, at time 3, for example, we see 8 particles. And all of them are to the right of the origin because we have assumed that our displacements are strictly positive, just for simplicity of presentation. So since we have assumed that, you see that all of them are to the right. This is origin, all of them are to the right of the origin. Now here is a statistic that you might be interested in. Rn is the position of the rightmost particle at time. And also ask the same kind of question about leftmost particle, but let me consider on the rightmost particle. Obviously here the length of Rn is this one, right? This is the rightmost particle in the third generation. So this is Rn at n equal to 3, this length. The question is, how fast does Rn grow as n goes to infinity? This is a very precise question. Now, what do I mean by how fast it grows? It's a random variable, right? So, okay, I'll tell you what it means. So here is the question restated. Now, this has already been looked at in the power law case. Richard Duret was a very famous probabilist. In 2 papers, actually the first paper was written in 1983 and second one 1979. It just shows that some journals delay so much that the first paper gets published later. In any case, these 2 papers, they showed that in the binary case, at least, the growth rate of this random variable Rn, which is the position of the rightmost particle, is 2 power n over alpha. So this n is this is when n is large, okay? When as n goes to infinity. So this is when n is large, it's like 2 power n over alpha. And then this 2 is coming from binary essentially. N, of course, is the number of generations. And alpha is the tail parameter. Remember the displacement d bigger than x was like x power minus alpha, right? Up to a constant. So that alpha is showing up here. More precisely, he showed that Rn divided by 2 power n over alpha converges in some sense to a positive random variable. And the sense is in the weak sense, like weak converges the distribution. I'm going to write down a precise statement later. Therefore, I don't want to, by the way, I have promised that I'm going to explain everything and I'm going to define everything in this talk. I to make it self-contained. I'm actually going to do it. So don't worry. I'm going to specify and tell you what this statement means later on, if you don't know what it means. But right now, just assume that Rn by 2 power n over alpha converges to a positive random variable in some sense. So which basically means since it converges to a positive random variable, it means that Rn is growing like 2 power n over alpha. So that's all you need to understand. Now, instead of the rightmost particle, I can ask the same question for the second rightmost particle. So what is that? So you look at all the particles. Here in generation 3, there are 8 particles. So you look at if you go from left, you look at the 7th particle. So this is the second rightmost particle. How far that is from the origin? What is the position? You can ask the same damn question about that guy too. I'm going to call it Rn2 for the second rightmost particle. Now, how does it grow? Now expect that's one other thing. That's of course one question. Another thing is, how does the gap statistic grow? So this is called the first gap statistic. So this is the difference between the rightmost particle and the second rightmost particle. By the way, all of these rightmost particle, second rightmost particle, as if you're a statistician, you know that I'm talking about ordered statistics. So difference between 2 or successive ordered statistics is called a gap statistics. Example, position of the rightmost particle minus position of the second rightmost particle. That's the first gap statistic. So here, this distance is the first gap statistic. This one would be the second gap statistic. This distance would be the third gap statistic, and so on. Now I'm asking, what happens to the first gap statistic? How does it grow? Now you would expect that since the entire system, especially the rightmost point, is growing like 2 power n over alpha, the entire system most probably is growing. This is just a conjecture, but it's a very educated guess, is that, the entire system is growing like 2 power n over alpha. In that case, you would expect that, okay, maybe the second rightmost particle as well as the gap statistic, all of them are growing like that. That's not a bad guess to make. The guess is actually correct in this case. But the question, of course, is what happens in the long run? So in other words, can you find limits? Okay, forget about the word weak here if you don't know what it means. Where, after scaling by 2 power n over alpha, where does the second position of the second rightmost point converge to in distribution? And in some sense, it should converge to a positive random variable if there is any truth in the world. But what is that random variable? Can you find the distribution function of that random variable, or the density function of that random variable for that matter? Okay. Similarly, you can ask the same question about the first gap statistic. You look at the gap statistic, divide by 2 power n over alpha. Let n go to infinity in its in its own will, and then what is the limit? Can you find the limit? All these questions. So all these questions are important questions for physicists. By the way, gap statistic has a lot of meaning in physics. I don't know very well, but for example, gap statistics can, depending on the situation, it can relate to various energy levels, energy barriers, etc., etc. I'm not a physicist, so I don't know. But if you talk to any statistical physicist, they'll talk about this. By the way, I should tell you this little bit of trivia here. This word statistic, this phrase statistical physics has a lot of Indian connection. Even before anything else, if I look at classically, there was an Indian physicist whose name is attached to statistical physics. Can anyone guess who he or she is? I think somebody has answered it correctly. Yes, S.N. Bose. Very good. So S.N. Bose and Albert Einstein, they have their name together in something called Bose-Einstein statistics. Okay, Bose-Einstein statistics, not statistics, sorry. So this Bose-Einstein statistics is an example of statistical physics. I would say it's a classical example of statistical physics. Similarly, there are other models, Fermi-Dirac statistics and Maxwell-Boltzmann statistics. These are all important models. Talking of Boltzmann, there is a medal called Boltzmann Medal, which is the highest honor for a statistical physicist. By the way, what is statistical physics? I didn't tell you. It's a branch of physics that uses statistics the most. So this is the branch of physics that uses probability and statistics. The models are random and probability and statistics are needed in order to analyze the models. Now, I would say a very generous algorithm for getting papers published in the best journal of probability, namely best journals of probability, namely Annals of Probability, Probability Theory and Related Fields, AIHP, etc., is the following. You go to a statistical physicist paper, they have predicted many things. You just prove them formally using mathematical knowledge. Mathematical notation, formally meaning, formally as in a mathematician, the way a mathematician will prove a theorem. If it's a sufficiently famous physicist and it's a good enough conjecture, which is hard enough to prove, it's a sure shot of Annals of Probability paper. I'm presenting it like an easy algorithm, but it's not so easy because proof might be very difficult. But this is a standard way of getting papers published in those journals these days. Not just Annals of Probability, even Stochastic Process and Applications, EJP, all these journals, Annals of Applied Probability, all these journals, a lot of papers are actually proving theorems related to physicists' conjectures. Okay, so what is BEC? I don't know. Can you tell me? Unmute yourself and tell me.
Bose-Einstein condensate. That's the experiment.
Oh, condensation. Yeah. That's related to Bose-Einstein statistics.
That's right.
Yes. Okay. Thank you.
Sure.
Okay. So are you from physics by any chance?
No, I'm not from physics, but I've heard the concept. Yeah.
Okay. Thank you. Okay. So anyway, if I'm not wrong, you must be one of the organizers. I think you were.
That's right. Well, thank you for thank you so much. Yeah.
Yes, I remember that. Yes. Anyway, I don't know you, but maybe someday I'll meet you. Okay. So anyway, so the point is that we want to, and then talking about Boltzmann, so this Boltzmann medal, there has been a physicist from India who won the Boltzmann medal, and he's the first Indian to win the Boltzmann medal, the best honor for a statistical physicist. Can anyone name the person? It's a physicist from India. He is a physicist from India. So he worked in Tata Institute of Fundamental Research, Mumbai, more or less throughout his life. And now he's in IISER Pune. Dr. Deepak Dhar, exactly. Professor Deepak Dhar, Dr. Deepak Dhar, he is the one. Okay, so he won the Boltzmann medal. So statistical physics has a rich tradition in India. So does probability, by the way. Okay, fine. So now the question is how to solve all of these problems. Okay. Now, one method would be brute force method. What do I mean by brute force method? I mean that you use different techniques, brute force techniques, okay? You have a lot of power, you use it like this, okay? And you solve each problem in a different method. It's not bad. It's still solving the problems. But the problem is it may not be elegant. More importantly, it may not be efficient because you have to attack each problem separately. It's always better to find a machinery that can solve a lot of problems. And that's what is called, in this case, point process technique. This is like a master key which can open many locks. Okay. Now the point is, we shall see a glimpse of method 2 in this talk. Now, why do I say glimpse? That's because we shall happily sweep many technicalities under the carpet. Because if we don't do that, I have to give a 2-hour talk, which neither Jyotishko nor Sharik nor Arvind will be happy about. So I want to finish in 1 hour. It's early morning for the people in USA, and it's a very late evening for the people in India. So somewhere in between for people in Europe. So let's not waste too much time on technicalities like weak convergence for unappropriate spaces, etc., etc. Tightness, vague metric, all these things I'm putting under the carpet, and that's why I've used this ash color so that you don't even see what it is. I'm trying to hide it from you. Okay. Any questions, comments, or concerns before I move on? Is a question? Okay. Okay, so this was more like a comment. Let's see. Yes, you can do that. So what the question says is that, would you mind asking the question by unmuting yourself?
Can you hear me?
Yes.
Okay, so the first model says that for each natural number, so each particle actually splits to say some other particle, or it just vanishes. So can this model be applied to a scenario when some particle just remains intact at some point? That means the generation is not same for all of the points.
So it means you are going to put a mass at 0.
Yeah,
right? In the distribution,
Yes.
displacement distribution, of putting a mass at 0, right?
Yes.
So you're making the particles lazy by putting, say, with probability P, the particle will stay put, or with probability 1 minus P will make a continuous movement.
Exactly.
Is that what you are saying?
Yes.
No problem at all. You can do that. You can make it lazy. You can make your particles lazy. No problem. It won't change anything. All these models, if you forcefully, because it won't change the right tail, it will only change the things near 0, and that won't affect anything in the extremes.
Oh, okay, okay. And continuity is a totally different.
Yes, there is a model in continuum also where the time can become continuous, and their model is different. It's called branching Brownian motion, where what happens is, in binary case, it would be like this. Every particle will come with an exponential clock. Every particle will wait after exponential amount of time and then split into 2 particles.
Okay. Sorry,
okay? So you'll start with 1 particle, which you wait for an exponential amount of time. The moment exponential clock ticks, it will branch into 2 particles. Each of those 2 particles will come with their own exponential clock, and then they will branch after the clock ticks and so on.
Okay.
Okay, this is how the model is described in the binary case. And this is called branching Brownian motion, which is a related model. Very good questions.
Okay.
Sorry, in that case, I will ask maybe a pedantic question, because we do not know how it operates near 0. So if it allows something like a mass at some things like 0, 1, 2. So this may be pedantic, but what happens if 2 particles overlap? Do we only see 1 particle?
So in this particular case, I'm assuming that even if say without loss of unity, you assume that there is a continuous distribution, at least towards the right. So after some point, it's continuous, so that they don't collide. So we just assume that they don't see the same point. Even if it does, in the limit, it won't change anything, because we are dividing by n, etc. So binomial distribution, discrete distribution, but when you scale it, it becomes continuous distribution.
Right.
Similarly, here also, even if you assume things are discrete, once you scale things, it will become continuous. So it won't matter. That's a good question, by the way. It's a very good question. Anything else? So if not, so let me move on. So I've been talking about weak convergence. Let me just tell you at least weak convergence for discrete random variables. So let me assume that my random variables un are all sequence of even are all random variables which are taking non-negative integer values. So for example, geometric, Poisson, negative binomial, all those known distributions that we know in discrete case are all like that, right? It takes non-negative integer values. Now, it doesn't have to be non-negative integer, but for simplicity, I assume that. And suppose u infinity is another such random variable. By the way, I'll follow this convention. Whenever un converges to something, I'll call it u infinity. Just a notation. There's nothing to do with infinity here. I'm just letting you know that I'm taking n go to infinity, so un is converging to infinity. Now, this is what I was talking about, weak convergence or convergence in law or convergence in distribution. Un converges in distribution to u infinity if and only if for every non-negative integer k, the probability that un takes the value k converges to the probability that u infinity takes the value k. So for every fixed k, positive non-negative integer, okay, this convergence happens as n goes to infinity. Now, this is a theorem of Scheffé. It's called Scheffé's lemma, but I'm presenting the discrete version of that. The proof you can find in various texts. That is the continuous case, the proof is there. In discrete case, the proof just mimics the continuous case. But for me, just assume this as the definition of weak convergence. This meaning the red part here. I say un converges to u infinity in distribution if for every non-negative integer k, un equal to k converges to infinity equal to k. This is only for non-negative integer value random variables, because I'm going to now talk about this kind of convergence. That's why I wanted to tell you. So in other words, you can think of for discrete random variables, instead of convergence in distribution, just think of convergence of probability mass functions. This is a probability mass function of un at the point k that should converge the probability mass function of u infinity at the point k. That's all I'm saying. Is the definition clear? We think of it as the definition, as I said. Okay. Now, what is the master key? I should tell you, I've been telling you master key, master key, master key. What is it? Fix an x. Since the entire system is going like 2 power n over alpha, you look at the following sequence of random variables. Now, here is the point. Think that I have a microscope. I'm looking at things through a microscope. I have the point x, but I have a microscope which magnifies everything by the order of 2 power n over alpha. Why? Because that's exactly how the system is growing. So I want to see the thing under microscope. So I took a point x, I saw it under the microscope, so the point becomes 2 power n over alpha times x. Now I want to see how many of these particles in the nth generation are to the right of this x seen at the microscope. Okay? Alternatively, you may say the entire freaking system is growing like 2 power n over alpha. So I'll divide everything by 2 power n over alpha and then see after dividing how many of them are to the right of x. Same thing. Either of them is okay. So either you look at the original system and then you fix the point x, look at the point 2 power n over alpha times x and see how many particles are to the right of it. Here in this picture, the generation is 3 still. So there are 8 particles. If this is 2 power n over alpha times x, then the number of particles in the nth generation that are to the strictly right to this point star is 1, 2, 3, 4, 5. So therefore, this is 5. Okay. So this denotes the number of particles at time n that are strictly farther away from 2 power n over alpha times x. Is the definition clear? I'm doing it for a fixed x, say. At the moment, x is fixed. So my star is fixed. I'm just counting how many particles are to the right. Now, clearly, each of these guys is a discrete random variable. And for a fixed n, it takes the value 0 up to 2 power n. X is fixed, so don't change x for now. Now, even if further, if you fix n, of course, there are 2 power n many particles at the most. So, of course, this is taking values from 0 to 2 power n. As n goes to infinity, this is going to take all non-negative integer values, right? 2 power n is going to infinity. So it's going to take all possible non-negative integer values. But the question is, can you find the weak limit of these guys as n goes to infinity? Fixing an x. You fix an x, look at the number of particles that are to the right of the star. Now let n go to infinity. Can you find the limit of this guy? Of course, there is no guarantee a priori that, that is going to have a limit. But since the entire freaking system is growing like 2 power n over alpha, this will have a limit. That's the whole point. Okay, so this will have a limit. Suppose it has a limit, and again I follow the convention. My x is fixed, so my x I'm not doing anything. I'm letting n go to infinity, so I'm putting infinity there. So suppose for each fixed x, you know, n comma x is converging in distribution or converging weakly to n infinity comma x. Okay. Now, how does it help me? In other words, last slide was about what is the master key. This is the master key, finding this limit. The question is, why is the master? Now, let's go back to Duret's work, Duret related work. Suppose I want to find the scaling limit of the rightmost point. That's same as asking, what is the probability? Okay, so scaling limit meaning for each fixed x positive, I want to compute after scaling of Rn, this is less than equal to x. I'm finding the distribution function of Rn divided by 2 power n over alpha. Okay, I'm looking at that. And then I want to take limit as n goes to infinity for every fixed x positive. Okay. Now this is same as asking Rn is less than equal to 2 power n over alpha. Now I can rewrite everything in terms of this nnx. What is that? This is same as asking, so this is your 2 power n over alpha. The only way the rightmost point would be less than equal to 2 power n over alpha is if and only if all the particles that you see in that generation are to the left of 2 power n over alpha. So in particular, the number of particles that are strictly right to this green point here is 0. Nnx should be 0. Is that clear? Why this equality holds? Any question? If that is the case, then of course, because I have already found out this limit, suppose somebody has given me this limit, then by just the 2 slides before I told you that convergence in distribution means convergence of probability mass functions. So probability of nnx equal to 0 should converge to probability of n infinity x equal to 0. And if we know the distribution of n infinity x, theoretically I can find out where this limit goes to. So that's how this is going to help. Of course, you would say, oh, what help? Professor Duret had already done it. What new are you doing here? Of course, I'm doing something new because I can also take care of the second maximum now. Think of the second maximum. Meaning, think of the second rightmost point. Position of the second rightmost point is Rn, remember? Suppose I want to scale Rn by the same quantity, 2 power n over alpha. And then I want to look at the probability that this guy is less than equal to x for a fixed x. This is same as asking the second rightmost point is less than equal to 2 power n over alpha times x. Now, one of the two things will happen. Either second rightmost point would be less than equal to x if and only if either all the particles are to the left of this 2 power n over alpha times x, or exactly one particle is to the right and all the other ones are to the left. Is that clear? This is the only way the second rightmost particle can be less than equal to 2 power n over alpha times x. Either all of the guys are less than equal to 2 power n over alpha times x. So therefore, the second guy is here, which is less than equal to this x, of course. After looking through that microscope, which magnifies things, right? I'm looking through microscope, right? Okay. And then otherwise, the second case is that one of them is to the right, but that's it. If the another one is to the right, then the second rightmost is to the right of this point. That's not allowed. So therefore, here also the second rightmost point is less than equal to this green point. So therefore, these are the only two possibilities. Is that clear? That means this probability that I have written here is either nnx is equal to 0 or nnx equal to 1. And these are disjoint events. So therefore, the probabilities will add up. And by virtue of Scheffer's theorem, this is now telling me that this is converging to the limit taking the value 0 and the limit taking the value 1, added up. And of course, if I know the distribution of n infinity x, then I can compute these guys. This is why this is the master key. Same thing can be done for the third maximum, fourth maximum, etc. Gap statistic, all those things can be sort of read out from this kind of things. Is this slide clear? I think this is the most technical slide that I have in some sense. Is this clear? Any question on this? Okay, so if not, I'll move on. Now I'm going to tell you the limit, how the limit looks like. So fix an x, defined for every n, nnx is the number of particles at time n that are to the right of x when seen under this microscope. Okay? Meaning to the right of 2 power n over alpha times x. As n goes to infinity, NNX converges to n infinity x in distribution where n infinity x has a particular form. What is the form? The form is like this. This is a sum, it's a random sum. It's a sum of Poisson many. Px is a Poisson random variable with parameter x power minus alpha, where alpha is the, what is alpha? Alpha is the tail parameter of the distribution. And sum of what? Sum of IID random variables, which are 2 power g1, 2 power g2, and so on. Each gi is a geometric random variable. Now, geometric has two conventions. Either it can start from 0 or it can start from 1. I'm using the convention where it starts from 0. Okay, so let me write down the limit once more because the limit is very important. The limit looks like, so this is the limit of NNX as n goes to infinity, the weak limit. Okay, this looks like this, where G1, G2, G, etc. are IID geometric half. And as I said, it starts from 0. So its probability mass function is given by this quantity. So this is basically same as the following. You have an unbiased coin. You toss the coin. Number of tails before your first head follows this distribution. Okay? So that starts from 0. Similarly, the random variable Px takes, this is a Poisson random variable with parameter x power minus alpha, where x is the point that you're looking under microscope. So x is the point to the right of which you're counting the number of particles. So this x, 2 power n over alpha times x, that is. So this is that x. So that x and the alpha from the parameter is coming here in this Poisson. In a particular, the Poisson PMF is looking like this. I told you, I promised you, I'll introduce Poisson, geometric, everything. So I'm doing it. And all of these random variables have nothing to do with each other. Okay, they're all independent. Geometrics are all identically distributed as well. Poisson is different, but they're independent from all of these geometrics. Now, what does this random sum mean? It means that when Px is 0, Poisson can be 0, right? If Poisson is 0, then I'm summing from 1 to 0, it is 0 by convention. Okay, I mean 0. Okay, if Px is 1, then I just have one of them, 2 power g1. It's the distribution of 2 power g1. When Px is 2, then I have 2 power g1 plus 2 power g2, where g1, g2 are IID geometric, and so on. Okay, if Px is equal to 3, then it's 2 power g1 plus 2 power g2 plus 2 power g3, and so on. Now, any question, comments, or concern? Anything you want to ask? Is the limit clear? Okay. Assuming that it's clear, I'm giving you 2 exercise problems. First problem, show whatever Professor Duret had shown in 1979 and 83 using this method that I've already described to you. Go back to my slides, use the method that I've already described, and use the limit that I have given you, and show that Professor Duret was correct. Okay. Also show that second maximum, also this is the convergence distribution, by the way. For every positive x, find the limit of the distribution function, essentially. Okay. Show that the second maximum after second rightmost point position after the scaling converges to this distribution. By the way, this distribution has a name. This is called Frechet type extreme value distribution. It arises in extreme value theory. If anyone has seen it, you must have seen it in extreme value theory. This is not a standard distribution, but this is something we got in as limit. I love giving exercises, so I'll give you more. Suppose Rnk is the position of the kth rightmost particulars time n. Find the following limits: third maximum and fourth maximum. So third rightmost point and fourth rightmost point. You'll say this is getting boring, man. You're asking the same damn question over and over again. But there is a point here. The point is, what happens for a general k? And as you will see, something very, very, very number theoretic will come into the picture. Partitions of k as sums of powers of 2 will become important. I don't want to tell you exactly how. If you solve the second exercise here, which is the fourth exercise that I have given you, then you will see exactly how. Okay? I don't have to tell you exactly how. Okay? So do solve these exercises. I've given you enough hints so that you can solve these exercises. So I've given you one problem as icebreaker and 4 exercises which are related to this talk. So I've given you 5 exercises. Okay, fine. Now let me go back to this tree representation. As I told you in the beginning, and somebody had rightly observed, is that here we have a tree representation, but every vertex denotes a particle. For example, this vertex, this green vertex is a particle. Now it produces two offspring. One of them is this blue particle. Again, that produces two of them. One of them is this green one. Again, that produces two of them, which one of them is the yellow one. So each vertex actually denotes a particle in this representation. Now you can identify each edge with the vertex that is below, which is away from the root. Okay. So for example, this green vertex, I'm not colorblind. This orange vertex can be identified with this orange edge. Similarly, this green vertex can be identified with this green edge and so on. So what does this identification help you with? Attach IID power law displacement on each edge. Each of them you attach independent, all of these guys, all of the edges, you attach independent power law displacements. Now remember, each edge is identified with a particle. Each edge is identified with a vertex, the vertex below, and the vertex is identified with a particle. So therefore, each of these displacements is actually the displacement of the corresponding particle. That's all. Okay. Now, as somebody rightly observed, position of a particle is first of all position of its parent plus its own displacement. And by induction on n, the generation size, you can show that this is the sum of the displacements on the unique path from root to that vertex. Namely, for example, if you look at this yellow particle, you look at the entire path that I have colored here, namely this orange edge, followed by the blue edge, followed by this green edge, followed by this yellow edge. Each of them has a displacement attached to it, which corresponds to the corresponding particles. Sum all of those displacements. That's going to give you the position of the particle. Now, when I'm saying unique path from the root, I mean unique non-backtracking path. Only mathematicians can think of backtracking in such a path, so don't worry about it. I'm just saying unique geodesic path from here to here, okay, without backtracking. Okay, so position of a particle is the sum of the displacements on the unique path from the root. That's the bottom line, which has been observed in my second slide by somebody, I think, the first slide maybe. Good. Now I'm going to tell you some heuristics. It's good to do some heuristics, even though I'm not going to give a proof, but you can do some heuristics. Why Poisson? Poisson is at some level, Poisson is coming from binomial converging to Poisson distribution. So we all know if n times Pn converges to lambda, something positive. So, okay, so if lambda should be positive, by the way, I didn't write it, that's a typo, but lambda is positive. Then binomial n positive and less than infinity. So then binomial n comma Pn converges in distribution to Poisson lambda. Okay, so I'll finish quickly. That's where the Poisson is coming from. I'm not going to tell you more than that. Okay, a little bit more I'll tell you. Okay, so why geometric? Geometric is coming from the following. Run a binary tree up to n generation and choose an edge at random. Let ln be the number of descendants of the chosen edge in the nth generation. So here is the picture. So here n is 4. So I have run the whole dynamics up to 4th generation. Now then I have chosen, there are so many edges, right? There are how many edges are there? 2 plus 4 plus 8 plus 16, many edges. What is that, by the way? That's 31, right? Yeah, there are 31 edges here. I've chosen one of these 31 edges at random. So it so happened that this particular edge was lucky, this red edge. So I chose that one. Then I saw, okay, in the last generation, which is 4th generation here, how many descendants does it have? Here it's 4. In general, I'll run this tree up to nth generation, and then I'll choose one of the edges at random and look at how many descendants it has in the nth generation. If n goes to infinity, you can show that this converges to a 2-power geometric random variable. That's where the 2-power geometric random variable is coming from. Okay, this is another exercise. This is your 6th exercise that I'm giving today. Sorry for giving so many, but this is an easy exercise, trust me. Okay, so from there it's coming. Now I can tell you the little bit more. Basically, what is happening is, say you want to know about the rightmost particle. That means it can be shown mathematically that The rightmost particle is large because one of the displacements was very large. Well, with very high probability, one of the displacements are very large. More generally, one of the Poisson many is very large. Anyway, let's not go into that. Now, the point is, this one is called one large jump in heavy tails, but power law distributions. Now, then that one is IID among all of them, because these are all IID, all the displacements. And then you have to look at how many. So if this is large, if this displacement of this particle is large, all of its descendants will be very far away from origin because of this large displacement. So that will contribute in the rightmost particle's position. So that's the idea. And then, that's where this geometric is coming from. And then, how many of them are going to be large in the long run is a Poisson random variable. One is just as an understatement. What actually I mean, Poisson many are going to be large. Okay, and that's where the binomial converging to Poisson will come in from, roughly. So let's not go more into it, but this is the intuition. Now, a few remarks. If each particle produces m offsprings as opposed to 2, so m is bigger than or equal to 2, by the way, there's no point talking about 1, then each 2 power gi is going in the limit will be replaced by m power gi. More generally, branching happens according to a branching process with a finite progeny mean mu. Then 2 power gi will be replaced by mu power gi. Okay, the displacements need not be positive. You can also handle negative displacements. You have to assume that the tails are balancing, etc., etc. Those things I'm not going to get into. Asymptotics of gap statistics also were investigated, and this was asked by statistical physicists, very famous statistical physicist actually, Gregory Fair, in a conference to Ion, my student, and then we answered this question as well. Two conjectures of two very famous statistical physicists actually, Brunet and Derrida. By the way, Bernard Derrida also got the Boltzmann medal earlier. Eric Brunet is yet to get it, but he may get it as well at some point. So Brunet and Derrida made two conjectures, and we have actually verified this in our setup, linking our work with this particular work that I have written here. Now we have extended this work to various situations, dependent displacements, multi-type case, infinite progeny mean, etc., etc. All of these are basically going to come in the references. I'm going to put that out. And there are many open problems that we can work on. In particular, since it is IISA, I should give something statistical. Any statistical inference and branching random walk is open. For example, if you look at the particles in the nth generation and try to estimate alpha, that's a very difficult problem. That's because you don't know the progeny. You don't know the genealogy. You just look at the particles. It's a very difficult problem. Okay, so there are other problems too that are written here. And I think that's where I would like to stop. These are the references. This is the paper I mainly talked about. These are the other ones. This is the dependent case. This is the multi-type case. This is the infinite progeny mean case. So I'll share the slides with Jyotishko, so you'll be able to see everything. So thank you very much, and please stay safe.
Thank you. Thank you so much for the excellent talk. Are there any quick questions? We're running out of time, but if there is any quick question, we can probably take it.
I have a question not related to this particular theme, but one of the tools. What was referred to as Sheff's lemma. Now, for a discrete distribution, point-wise convergence of the PMF, which is really the PDF with respect to counting measure, will immediately give you strong convergence and hence weak convergence.
Yes.
But coming from weak convergence to point-wise convergence of the PMF, that is a characteristic function argument that I can think of.
No, you just do it from definition.
We just do it from definition.
Yeah, but weak convergence means the convergence of the CDFs at the limit, at the points where the limit random variable is continuous, right?
Right.
So just use that definition from
okay,
there.
So look at the jumps. Okay.
Yes. From there you can
have differences. Okay.
Yes. To be honest, I mean Shumanda is right. So this is Shumanda from Connecticut, right?
Yeah.
Yes. So he was by the way, he was my professor in statistical methods 1. Thanks for coming, Shumanda. Okay. So he taught us first course in statistics at ISI. So anyway, yes. So Shumanda is right. One direction is officially Sheff's lemma. The other direction is you can do it directly. So you're right. Officially, the other one is Sheff's lemma. So in the continuous case, the Sheff's lemma says that if the density function converges pointwise, then weak convergence holds. Yes.
Thank you.
Yes, thank you, Shumanda, for the question.
Okay, so I think we are already past the time limit. So let us thank the speaker once again. Thank you, Parthanil, for this wonderful talk. And so we'll meet in a month's time with another speaker. And thank you. And I just like to end with a note that if you are a student and if you want to become a member of IISA, the membership is free. And please contact one of us for if you need more information about that. Thank you so much. Thank you, Professor Roy, for the wonderful talk, and thank you for everyone for being here. Okay,
so I think there was something in the chat. Can I just quickly read it? So Iman, would you mind telling me what is the typo?
Basically saying that it should be
It's
discrete.
in the theorem header. It should be discrete. It's written decrete.
Oh yeah, thank you. Theorem header, I didn't see. Thank you. It just shows that I have put it today. So yeah, I put it today just to. Thank you for catching it. I'll definitely do that. There are some things that I didn't mention, alpha positive, etc., etc. I have to do that too. So yeah, so Jyotish, you have raised your hand.
No, I have not. I'm just.
You're saying bye. Is it? Oh, you're saying bye. I think. Okay.
It's a clapping. So thank you again for the.
Okay. Yeah, okay. And thank you so much for inviting. So it was a pleasure and honor. Okay. The audience was quite broad. My students and my teacher, everything, my professor, everything. So yeah, very nice. Everyone was there. Thank you so much for coming.
Thank you.